Hello! In this video, we are going to prove the following theorem. The square root of 1 plus the square root of 1 plus the square root of 1 plus the square root of ... is equal to the golden ratio. Now, really, what's going on here is we have a sequence whose first term is the square root of 1, whose second term is the square root of 1 plus the square root of 1, whose third term is the square root of 1 plus the square root of 1 plus the square root of 1, and so on and so forth. So what we're really saying here is the limit of this sequence as n approaches infinity is equal to the golden ratio. So this is really what we're going to be proving. Now, we can talk about what this sequence is more carefully by defining it recursively. So again, the first term of our sequence is the square root of 1. Also, if we're given any term of our sequence, then to compute the next term, all we have to do is add 1 to this and then take the square root. Now, this definition for our sequence is well defined because notice the first term of our sequence is positive, and if we're given any term of our sequence which is positive, then the next term of the sequence will be positive as well. Because, well, if we say xn is positive, well then 1 plus xn will also be positive, so we can take the square root of it. And the square root of a positive number is positive. Therefore, the next term of the sequence is positive. Right? This shows that our sequence, or this definition, is well defined because we'll always be able to perform this square root operation. Okay, so now let me just write this up here. We want to show that the limit of this sequence is equal to the golden ratio. Now, before we deal with anything that has to do with the limit of this sequence, first we're going to show every term of our sequence is greater than or equal to 1, because that's going to be useful later. And so to show this, we're going to use induction, right? We're really trying to show for all positive integers n, xn is greater than or equal to 1. And so let's start with the base case. In the base case, we're trying to show that the first term of our sequence is greater than or equal to 1. In other words, we're trying to show that x1 is greater than or equal to 1. Well, x1 is equal to the square root of 1, which is equal to 1. So immediately we have x1 is greater than or equal to 1. So we're done. This completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary term of our sequence, say xn, and we assume xn is greater than or equal to 1. The whole goal is to show xn plus 1 is greater than or equal to 1. Now, notice, if we take this inequality and add 1 to both sides, we get 1 plus xn is greater than or equal to 2. And now, since both of these guys are positive, well then if we take the square root of both of them, the sign of the inequality will remain the same, right? That's a property of square roots that we're going to use here. So really, this implies that the square root of 1 plus xn is greater than or equal to the square root of 2. And the square root of 1 plus xn is equal to xn plus 1 by definition of our sequence. And we know that the square root of 2 is greater than 1. So xn plus 1 is greater than or equal to 1. And that was the whole goal of the induction step, right? Given any term of our sequence is greater than or equal to 1, it follows that the next term is greater than or equal to 1. And so what this establishes by induction is that every term of our sequence has to be greater than or equal to 1. And so this proves what we wanted to show. And so since we ran out of room, we're going to move back up to the top. Now remember, the whole goal is to show that the limit of this sequence is equal to the golden ratio. But before we show that the limit of this sequence is equal to the golden ratio, we're first going to show that this sequence actually has a limit. And then we're going to show that that limit is equal to the golden ratio. Now, to show that this sequence has a limit, we're going to use the Monotone Convergence Theorem, which says that every increasing sequence of real numbers that is bounded above has a limit. In fact, there's a similar statement for decreasing sequences of real numbers. But now, what we want to do is we want to apply this theorem to show that this sequence has a limit. So what we want to show is we want to show that our sequence is increasing and our sequence is bounded above. Now, we're first going to show that our sequence is bounded above. In particular, we're going to show that our sequence is bounded above by the golden ratio. In other words, we're going to show that every term of our sequence is less than or equal to the golden ratio. In fact, we could actually show every term of the sequence is less than the golden ratio. And so we're going to show that by induction. So let's start with the base case. Now the first term of our sequence is 1, right? X sub 1 is equal to 1. So really we want to show that 1 is less than the golden ratio. Well, let's note that square root of 5 is bigger than 2. And therefore, if we add 1 to both sides, we get that 1 plus square root of 5 is greater than 3. So then, if we take this inequality, divide 2 on both sides, we get that the golden ratio is greater than 3 halves. And 3 halves is bigger than 1. And 1 is equal to x1. And this shows that the first term of our sequence is less than the golden ratio. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary term of our sequence, and we assume that that term is less than the golden ratio. The whole goal from here is to show that the next term of our sequence is less than the golden ratio. That is, we want to show that xn plus 1 is less than the golden ratio. Now, to show that xn plus 1 is less than the golden ratio, we're actually going to show that xn plus 1 squared is less than the golden ratio squared. And so, to show that, well, let's consider writing out the golden ratio squared. Well, we know that the square of a fraction is just the square of the numerator over the square of the denominator. And if we expand out the numerator, it's just going to be 1 plus 2 squared root of 5 plus 5. And 2 squared is just 4. And then we can simplify the numerator to 6 plus 2 squared root of 5, all over 4. And then we could further simplify this to 3 plus square root of 5 over 2. And then it's not too difficult to see that this is just equal to 1 plus the golden ratio. But now, since the golden ratio is greater than xn, it follows that 1 plus the golden ratio is greater than 1 plus xn. And from the definition of our sequence, if we take the second equation that we have here and square both sides, we get that xn plus 1 squared is equal to 1 plus xn. And so what this chain of stuff establishes is that xn plus 1 squared is less than the golden ratio squared. From here, it follows that xn plus 1 is less than the golden ratio. The reason why is because of that property of square roots that we used before, right? Since both sides of the inequality are positive, it follows that if we take the square root of both sides, the sign of the inequality will remain the same, right? The square root of the left-hand side is actually just equal to xn plus 1. The square root of the right-hand side is just equal to the golden ratio. So xn plus 1 is less than the golden ratio. So, putting this together, we supposed inductively that we have a term in our sequence that is less than the golden ratio. From there, we were able to show that the next term must be less than the golden ratio. And so what this induction argument tells us is that every term in our sequence is less than the golden ratio. So indeed, our sequence is bounded above by the golden ratio. So we've shown that our sequence is bounded above. Now all that's left to show is that our sequence is increasing. Now, to show that our sequence is increasing, what this means is we want to show that every term in the sequence is less than or equal to the term that comes after it. In other words, we want to show for all positive integers n, xn is less than or equal to xn plus 1. Right? Because this will guarantee x1 is less than or equal to x2, is less than or equal to x3, is less than or equal to x4, and so on and so forth. In fact, we could actually show that this sequence is strictly increasing. So we're going to show for all positive integers n, xn is strictly less than xn plus 1. So we're trying to prove a statement about all positive integers n, so let's give ourselves an arbitrary positive integer n. From here, we're going to show that xn is less than xn plus 1. Now, what we're actually going to do in order to show xn is less than xn plus 1 is we're actually going to modify this slightly. To show xn is less than xn plus 1, it suffices to show xn squared is less than xn plus 1 squared. But xn plus 1 squared is equal to 1 plus xn. And then if we subtract xn to the other side, well then this is equivalent to this. And then if we factor out xn, this is equivalent to this. So if we have shown that this inequality is true, then we will have shown that this inequality is true, because these are all equivalent. But then if we've shown that this is true, well then by the property of square roots that we've been using, this implies xn is less than xn plus 1. So we're going to show that this inequality is true. And to show that this inequality is true, well, it's going to be useful to use the first two facts that we proved. Let's note that xn is greater than or equal to 1, but not only is xn greater than or equal to 1, but xn must be strictly less than the golden ratio, because we showed every term of our sequence is less than the golden ratio. Right? But then, if we take this inequality and subtract 1 on all three sides, we're going to get 0 is less than or equal to xn minus 1, which is strictly less than the golden ratio minus 1. Now, this is just equal to -1 plus the square root of 5 over 2. So now, let's take advantage of these two inequalities to show that this inequality is true. Now, if we write out xn times xn minus 1, well, notice, since xn minus 1 is greater than or equal to 0, if we take xn minus 1 and multiply it on both sides of the inequality xn is less than the golden ratio, the sign of the inequality will remain the same. And we're going to get that xn times xn minus 1 is less than or equal to the golden ratio times xn minus 1. But then, since the golden ratio is greater than 0, if we take the golden ratio and multiply it on both sides of this inequality, we're going to get that the golden ratio times xn minus 1 is less than the golden ratio times this guy. And then, if we simplify this, we're going to be multiplying the numerators and multiplying the denominators. Well, in the denominator, we're just going to have 2 times 2, which is 4. But if you multiply what we have in the numerators, well, it turns out the numerator is just equal to 4. And that's just equal to 1. So we have that xn times xn minus 1 is strictly less than 1. From here, it should follow that this inequality is equivalent to saying xn squared is less than xn plus 1 squared, right? So if we distribute xn across, we get this, and then if we add xn to the other side, we get xn squared is less than 1 plus xn, and 1 plus xn is equal to xn plus 1 squared. So we have xn squared is less than xn plus 1 squared. But then, using the property of square roots we've been using, we take the square root of both sides of the inequality, the sign of the inequality remain the same. We get xn is strictly less than xn plus 1. So, we have shown, given any positive integer n, we have xn is less than xn plus 1. And so that establishes x1 is less than x2, which is less than x3, which is less than x4, and so on and so forth. This shows that our sequence xn is strictly increasing. And now that we know that our sequence is increasing and bounded above, we can apply the monotone convergence theorem to say that our sequence has a limit. And so we're going to say that L is the limit of our sequence. Now there's another thing that the monotone convergence theorem tells us about this limit. In fact, the limit of our sequence is going to be the least upper bound of the terms of our sequence. Right? This is another part of the monotone convergence theorem that I forgot to write up here. So since L is the least upper bound of our sequence, well, we know that L is an upper bound of our sequence. So every term of our sequence is less than or equal to L. In fact, you could technically show that every term of our sequence is strictly less than L, but that's not really important. What's important is every term of our sequence is less than or equal to L, so in particular, x1 must be less than or equal to L. Well, x1 is equal to 1, so 1 is less than or equal to L. Right? L is greater than or equal to 1. Okay, now the whole goal from here is to show that this limit is in fact equal to the golden ratio. So that's what we're going to do next. Now, to show that L is the golden ratio, let's notice, given any positive integer n, this equation is true. Well, if we square both sides, then given any positive integer n, we have that xn plus 1 squared is equal to 1 plus xn. And now, since these two guys are equal for all positive integers n, well, if we consider the sequences xn plus 1 squared and 1 plus xn, these two sequences are equal because all their corresponding terms are equal. Right? So if these two sequences converge, they must converge to the same value, right? Because they're the same thing. So then what do these sequences converge to? Well, let's note, we know that xn converges to L. Well, a property of limits tells us that every tail of the sequence, xn, will also converge to L. So in particular, the sequence xn plus 1 will also converge to L. In fact, you can think of xn plus 1 as though we basically just removed the first term from our original sequence. So as you can imagine, the end behavior will be the same. And then let's use another property of limits. For instructional purposes, I'm going to write the same thing again. We actually have a product rule for limits, which tells us if we have a sequence converging to a limit and another sequence converging to a limit, then the product of those two sequences will converge to the product of those two limits. And so xn plus 1 squared must converge to L squared. So really, this sequence will converge to L squared. Okay, so then what does this sequence converge to? Well, again, let's note xn converges to L. Constant sequence of 1s will converge to 1. And then we have an addition rule for limits, which tells us if we have a sequence converging to a limit and another sequence converging to a limit, then the sum of those two sequences will converge to the sum of those two limits. So the sequence 1 plus xn will converge to 1 plus L. So this sequence converges to 1 plus L. Now, these two sequences are equal, so their limits must be equal. So L squared is equal to 1 plus L. So now, all we've got to do is take this equation and solve for L. Well, it's a quadratic equation. So if we apply the quadratic formula, we have this, and then if we just simplify each of these three parts, we get L equals 1 plus or minus the square root of 5 over 2. So L is equal to 1 plus the square root of 5 over 2, or L is equal to 1 minus the square root of 5 over 2. But since L is greater than or equal to 1, L can't be equal to 1 minus square root of 5 over 2, because 1 minus square root of 5 over 2 is less than 1. And so we've shown that the limit of our sequence is equal to the golden ratio. And so this completes the proof. And so yeah, that's pretty much it for this video.